The Voyager 2 probe currently drifts through the silent cold reaches of the vast interstellar dark. This lonely titanium craft recently sent a faint signal back toward our small and distant sun. NASA engineers noticed a subtle shift in the data packets during a routine deep space check. This metallic traveler remains our most distant eyes, watching the quiet edge of the solar system. The solar wind stops here, and the pressure of the galaxy begins its slow, crushing embrace. Sensors recorded a strange increase in local plasma density that defied our previous standard physical models. Scientists at the Jet Propulsion Laboratory analyzed these peculiar numbers with a sense of quiet wonder. The cosmic rays are hitting the hull with more frequency than we ever thought was possible. We are learning that the boundary of our home is much more active than first imagined. These transmissions take nearly a day to reach the giant radio dishes waiting on the Earth. Every bit of information tells a story of a place where human light has never shone. The vacuum is not empty, but filled with the ghosts of stars that died long ago. Cold gas clouds swirl in the blackness, and the probe hums a low and steady song. We listen to the static for the secrets of the void that lies between the stars. The message from the dark is a gentle reminder of how much we have to learn. We watch the flickering lights of the console and wait for the next slow digital pulse. The journey continues into the infinite, and we follow the path of the pioneer into night. Far beyond the reach of our sun, the stars shine with a cold and steady light. We are looking back at the tiny blue dot through the eyes of a brave machine. The deep silence of the cosmos provides a peaceful space for our minds to wander today. If you enjoy these deep explorations in space, consider subscribing or hitting the like button. It really helps the channel grow and allows me to make content like this. Now we settle into the quiet rhythm of the dark as the journey moves slowly ahead. The ancient signals continue to pulse through the void toward the waiting ears of our planet. We find comfort in the vast scale of the universe while the craft enters the unknown. Your soul can drift among the distant nebulae as we ponder the depth of the void. You are moving at a speed that is difficult for the human mind to fully grasp. Yet out here, it feels like standing perfectly still. The sun is now just a particularly bright star, losing its dominance over the sky as you cross the heliopause. There is no wind here, only the thin, ghost-like pressure of interstellar ions brushing against the golden record. Voyager 2 has been traveling for decades, a small, persistent thought launched into the basement of the universe. The recent data is not a scream or a sudden alarm, but a soft, rhythmic deviation in the expected background noise. It is a warning in the scientific sense, a notification that the environment is changing in ways our theories did not predict. You are feeling the transition from the sun's protective bubble into the raw, unshielded medium of the Milky Way. The temperature of the plasma has risen, and the magnetic fields are twisting into unfamiliar shapes. It is a quiet threshold, a doorway made of light and energy that we are crossing for the very first time. This subtle shift represents the end of the heliosphere, a massive bubble created by the solar wind that has served as our cosmic nursery for billions of years. As the probe pushes forward, the familiar comfort of the sun's influence begins to fade, replaced by a cold, dense reality that exists between the stars. It is as if we have spent our entire history inside a brightly lit room, and for the first time, we are opening the door to look out into the dark, silent hallway of the galaxy. The measurements coming back to us are not just numbers. They are the fingerprints of an ancient universe. The plasma, which is the ionized gas that fills space, is behaving in ways that challenge our fundamental understanding of physics. Inside our solar system, this gas is hot and sparse, blown outward by the sun at speeds of over 1 million miles per hour. But here, at the very edge, that wind is slamming into a wall of interstellar gas. This collision creates a region of intense turbulence, a place where the particles from our sun are forced to slow down, pile up, and heat up. It is a chaotic dance of energy that marks the true border of our home. We are witnessing the struggle between the sun's fading breath and the overwhelming pressure of the interstellar medium, a vast sea of hydrogen and helium that has been drifting through the Milky Way since the dawn of time. As the probe traverses this invisible boundary, the magnetic fields are the first to tell the story of the transition. These fields, which usually flow in predictable, straight lines from the sun, are now beginning to wrap around themselves, creating massive magnetic bubbles that stretch for millions of miles. It is a turbulent froth, a cosmic foam that acts as the final layer of defense for our solar system. Beyond this foam lies the interstellar magnetic field, a force that originates from the collective energy of 100 billion stars. This field does not care about our sun. It follows its own path, guided by the rotation of the galaxy itself. When the probe's sensors detect this shift, it is a sign that we are no longer under the protection of our parent star. We are now truly in deep space, exposed to the raw, unshielded radiation that fills the void between the worlds. This radiation is the most significant part of the warning the probe sends home. Inside the heliosphere, we are shielded from the majority of galactic cosmic rays, high-energy particles that travel at nearly the speed of light. These particles are the remnants of massive stars that exploded in supernovae millions of years ago, sent screaming across the universe like microscopic bullets. Our sun's magnetic bubble deflects most of them, acting as a celestial umbrella in a radioactive storm. But as the probe leaves this bubble, the intensity of these cosmic rays begins to climb. The sensors are being pelted by bits of dead stars, recording the history of the galaxy in real time. It is a reminder that space is not empty. It is a graveyard of giants, filled with the energetic ghosts of everything that came before us. The transition is slow and methodical, a journey of inches across a landscape of billions of miles. There is no physical line in the sand, no signpost that says you have left home. Instead, there is only the gradual change in the weather of space. The solar wind, once a roaring gale, becomes a whisper. The density of the surrounding gas begins to rise, signaling that the probe is now entering the interstellar clouds that drift between the stars. These clouds are the birthplaces of future solar systems, the raw material from which planets and perhaps even life will one day be formed. By moving through this medium, the probe is essentially traveling back in time, interacting with the same kind of primordial dust that formed our own Earth 5 billion years ago. The communication with the probe during this phase is a masterclass in patience and precision. Because the distance is so vast, every command we send takes almost an entire day to arrive, and every response takes just as long to return. We are holding a conversation across the abyss, asking questions and waiting 40 hours for the answer. It is a testament to human engineering that a machine launched decades ago, powered by a small piece of decaying plutonium, is still capable of sending these delicate signals. The power is slowly fading, the heat is disappearing, and one by one, the instruments will eventually go dark. But for now, The probe remains our lone scout, sending back word of a frontier that no human eye will ever see in person. We are learning that the edge of our solar system is much more complex than we ever imagined. It is not a clean break, but a messy, overlapping region of transition. There are layers of plasma that behave like fluids and magnetic waves that ripple like water in a pond. The data shows us that the sun's influence is a living, breathing thing, expanding and contracting with the solar cycle. Sometimes the boundary is close, and sometimes it stretches further out into the dark. We are catching the heliosphere in a moment of change, watching as it interacts with the local interstellar cloud. This interaction is what creates the warning, the realization that our protective bubble is not an invincible fortress, but a fragile equilibrium maintained by the sun's constant output of energy. As the probe moves deeper into the interstellar medium, the silence becomes even more profound. The radio signals from Earth are becoming so weak that they are almost indistinguishable from the background noise of the universe. To keep the connection alive, our ground stations must use massive antennas and sophisticated algorithms to filter out the interference of 100 billion other stars. It is a fragile thread of light, the only thing connecting a piece of human history to its creators. When the probe eventually goes silent, it will not be because it has hit a wall or crashed into an object. It will simply be because it ran out of the breath it needed to speak. It will continue its journey as a silent monument, a ghost ship sailing through the interstellar sea for millions of years to come. The warning we receive today is ultimately a gift of knowledge. It tells us where we come from and what lies ahead. It reminds us that our sun is just one star among many, and that our solar system is a tiny island in a vast, energetic ocean. By understanding the transition into the Milky Way, we are gaining the map we need to one day venture even further. We are learning how to navigate the currents of the galaxy, how to shield ourselves from the radiation of the stars, and how to survive in a landscape that is fundamentally different from the one we know. The probe is showing us the way, one rhythmic pulse at a time, proving that even in the face of absolute silence, the human spirit of discovery can find a way to be heard. To understand the distance Voyager has covered, imagine you started walking the day the probe was launched in 1977. If you walked every single hour of every single day, you would still be on the very first inch of its marathon. If the distance to the edge of our solar system were the length of a vast, silent library, our entire world would be a single letter on the first page of the first book. The warning the probe sends is like a hiker noticing the air getting colder as they reach a mountain peak. It is a natural shift, a sign that the familiar valley is now far behind and a new landscape is beginning. When the probe detects a surge in cosmic radiation, it is like feeling the first spray of salt water on your face before you can even see the ocean. We use these small electronic pulses to build a map of a place we can never visit in person. It is a slow, methodical conversation between a machine and its creators, held across billions of miles of absolute silence. This silence is not empty. It is a pressurized frontier where the very breath of our sun, the solar wind, finally falters against the colossal weight of the galaxy. As the probe pushes deeper into this transition zone, the telemetry reveals a chaotic ballet of particles. For billions of miles, the sun has been a protective parent, blowing a bubble of ionized gas that shields us from the harsh environment of interstellar space. But here, at the edge of the heliosphere, that protection is thinning. The magnetic fields that once guided the probe's instruments begin to twist and snap like rubber bands under the immense pressure of the interstellar medium. We see this in the data as magnetic bubbles, frothing regions of space where the solar wind is compressed into a turbulent foam. It is a violent, invisible border. The probe's sensors record a sudden, sharp drop in the temperature of the surrounding plasma, while simultaneously registering a spike in the density of high-energy galactic cosmic rays, the remnants of ancient supernovae from across the Milky Way. This is the moment the hiker leaves the marked trail and steps into the primordial forest. Every bit of data we receive is a miracle of persistence, a signal so weak that it arrives with less power than the light of a distant star. By the time these pulses reach our deep space antennas, they have traveled for nearly an entire day at the speed of light, crossing a distance so vast that the sun itself has shrunk to a mere point of brilliance in a crowded sky. This distance creates a temporal ghosting. We are never seeing what the probe is doing right now, but rather what it was experiencing nearly 20 hours ago. If the probe were to strike a rogue grain of interstellar dust and vanish, it would be dead for a full day before we even knew it was in trouble. This reality forces the machine to be more than just a tool. It is a surrogate explorer with its own autonomous instincts, programmed to heal itself and navigate the dark without waiting for permission from home. As the probe finally pierces the heliopause, the ultimate boundary, the salt spray of radiation becomes a torrential downpour. The solar wind, which has traveled at supersonic speeds since leaving the sun's corona, finally grinds to a halt. This deceleration is governed by the balance of pressure between the thinning density of the solar plasma and the outward force of its velocity. When this outward force finally equals the inward pressure of the interstellar gas, the bubble can expand no further. This is the true edge of our home. Beyond this point, the probe is no longer a citizen of the solar system. It is a traveler in the interstellar sea, moving through a medium made of the debris of stars that died billions of years before our sun was even born. The instruments detect a change in the pitch of the space around it, a higher frequency vibration of plasma that tells us the gas is colder and more tightly packed than anything within our solar bubble. We are tasting the raw ingredients of the universe. Even as the probe's plutonium heart slowly decays and its internal warmth fades, it continues this lonely vigil. Its power generators lose a few watts of energy every year, forcing us to turn off its instruments one by one, like a lighthouse keeper extinguishing lamps to save the last of the oil. Soon, the methodical conversation will cease. The pulses will stop, and the silence will become absolute. Yet, the probe will not stop. It will drift for eons, carrying its golden record, a time capsule of human music, laughter, and thought into the heart of the Milky Way. It is a testament to a species that was small enough to be confined to a single planet, but curious enough to send its senses into the infinite dark, leaving a permanent footprint in the stars long after the sun that birthed it has gone cold. Now let's move outward to the very edge of the sun's influence, where the solar wind finally tires out. For millions of miles, the sun pushes out a stream of charged particles, creating a safe harbor for the planets. But eventually, this wind meets the interstellar medium, the matter that exists between the stars. Scientists call this the bow shock, a silent collision where two different worlds meet and mingle. Voyager 2 detected a wall of fire, a region of hot, dense plasma that acts as a barrier to the galaxy. We understand that this wall protects us from the harshest radiation of deep space, yet we do not know why it is shaped the way it is. The mystery lies in its thickness and its constant, slow vibration. We accept this uncertainty, recognizing that our bubble is breathing in the cosmic dark. This brings us to a larger scale, where the sun itself is just a traveler, moving through a galaxy that is far more active and crowded than the quiet void we once imagined. This wall of fire is not a flame in the traditional sense, but a massive accumulation of solar particles that have been compressed and heated to incredible temperatures as they collide with the interstellar wind. It serves as a shockwave, a celestial shield that absorbs the most dangerous energy the Milky Way has to throw at us. Without this boundary, the high-energy particles from distant explosions would flood our solar system, potentially stripping away the atmospheres of planets and making life as we know it impossible. We are essentially living inside a giant, magnetic cocoon, kept warm and safe by the constant heartbeat of our star. The vibration the probe detected is perhaps the most haunting part of the discovery. The edge of our world is not a static line. It ripples and fluctuates, responding to the invisible currents of the galaxy like the surface of an ocean. These vibrations suggest that the interstellar medium is pressing back against us with a force we are only beginning to calculate. The thickness of this region varies wildly, sometimes stretching for millions of miles and other times thinning out, leaving us more exposed to the elements of deep space. This constant movement is what scientists refer to as the breathing of the heliosphere. It is a slow, rhythmic expansion and contraction that follows the 11-year cycle of the Sun, a long-distance pulse that connects the heart of our star to the very edge of its kingdom. As the Sun moves through the Milky Way, it does not travel alone. It carries us with it, carving a path through a local interstellar cloud that is itself moving through the spiral arms of the galaxy. We are currently passing through a region of space that is relatively empty, but the data suggests that we are heading toward denser clouds of gas and dust. This journey takes millions of years, and the wall of fire we see today is just a snapshot of a much larger, ongoing struggle for balance. The shapes we see in the magnetic fields are the result of this motion. The heliosphere is not a perfect circle, but a long, trailing structure with a head and a tail, much like a comet soaring through the night. The uncertainty we feel when looking at these results is a reminder of our place in the universe. We have spent centuries looking up at the stars, but only recently have we actually touched the medium that exists between them. The probe is showing us that the galaxy is not a vacuum of nothingness, but a complex, fluid environment filled with its own weather, its own currents, and its own dangers. The Wall of Fire is the first major landmark on a road that leads to the rest of the universe. It is the final gate of our home, and as we pass through it, we are leaving behind the familiar physics of the sun and entering a realm where the rules are written by the collective gravity and energy of billions of stars. This transition challenges our technology to its absolute limit. The plasma in this region is so dense and the radiation so intense that the electronic components of our machines are under constant bombardment. Every signal that successfully makes it back to Earth is a victory over the entropy of the cosmos. We are listening to the final whispers of a traveler who has seen things no one else has, a traveler who is currently feeling the heat of the galaxy's edge against its metallic skin. The data tells us that the sun's influence is powerful, but not infinite. It is a local light in a very large dark, and the further we go, the more we realize how much of the story is still left to be told. By studying the way our bubble breathes, we are learning how to predict the long-term future of our solar system. We are seeing how the sun reacts when it hits a bump in the interstellar road and how the wall of fire adjusts to protect the inner planets. It is a dynamic, living system that has been operating for 5 billion years, and we are the first generation to ever see it in action. This brings us back to the realization that we are part of something much bigger than our own world. We are passengers on a star, protected by a wall of fire, moving through a galaxy that is breathing right along with us. The mystery of the shape and the vibration is not a failure of science, but an invitation to keep exploring, to keep pushing the boundaries of what we know until the dark is no longer a mystery, but a map. To understand that, we need to step back and look at the magnetic fields that drape across the galaxy like invisible silk. As Voyager 2 pushed through the boundary, it found that the magnetic field of the galaxy is much stronger than we anticipated. It is not a straight line, but a complex, braided ribbon of energy that tugs at the probe's sensors. Astronomers see this ribbon through radio telescopes, but the data from the probe provides the only touch we have ever had. There is a mild, unresolved mystery in how these fields interact with the sun's own magnetism without causing violent disruptions. It is a calm, steady tension that has existed for billions of years. We observe the data and realize that the void is actually a structured, organized web. This brings us further into the drift, where the scale of time begins to outweigh the scale of distance. This organized web is not a tangled mess of random energy, but a delicate architecture of magnetic filaments and charged particles that stretch across the light years. When we look at the maps created by our most powerful instruments on Earth, we see a giant ribbon of energy draped across the sky. Yet it is only through the sensors of our distant machines that we can feel the texture of this structure. It is like touching the surface of a giant, invisible tapestry that has been woven over eons by the rotation of the galaxy and the deaths of ancient stars. The tension between our sun and the galaxy is a silent struggle that defines the very boundaries of our existence. As the sun moves through the Milky Way at 500,000 miles per hour, it pushes against the interstellar magnetic field. Normally, you would expect such a collision to be violent, filled with explosive bursts of energy and chaotic radiation. Instead, the data reveals a surprising stability. The two forces meet and slide past one another in a graceful, fluid motion. We are finding that the interstellar medium is far more organized than we ever suspected. It possesses a grain, a directionality that guides the path of the sun and shapes the protective bubble that keeps us alive. This calm interaction suggests a deep, underlying harmony in the physics of the deep dark, a balance that has allowed our solar system to remain stable for 5 billion years while passing through vastly different regions of the galaxy. As the probe moves deeper into this magnetic web, we begin to lose our sense of human time. Out here, the ticking of a clock feels irrelevant. The distances are so vast that we stop measuring progress in miles and start measuring it in decades. We are entering the drift, a state where the machine is no longer just traveling, it is becoming part of the environment it was sent to study. The atoms of the probe are now being struck by the same particles that were forged in the hearts of stars that lived and died before our own world was born. We are seeing a scale of time that is almost impossible to comprehend. In this region, 1 million years is a blink of an eye, and the life of a human civilization is but a brief flash of light against an eternal background. The mystery of how these fields interact without disruption leads us to question the very nature of the vacuum. We used to think of space as empty, a simple stage where planets and stars played out their roles. But the data from the probe tells a different story. Space is a substance. It has density, it has memory, and it has structure. The magnetic fields are like the nerves of a giant organism, transmitting information and energy across the void. When the probe detects a slight change in the orientation of these fields, it is sensing a ripple in the fabric of the galaxy itself. These ripples might have started thousands of light years away, caused by the collision of two distant stars or the birth of a new nebula. We are catching the echoes of galactic history, translated into the language of electronic pulses. This realization shifts our perspective from that of a resident to that of a voyager. We are no longer looking at the galaxy from the safety of our porch. We are out in the street, feeling the wind and the cold. The organization of the Webb provides a sense of comfort in the face of such overwhelming scale. It suggests that even in the deepest parts of the universe, there are rules. There is an order to the chaos. The sun is not just a lonely wanderer lost in the dark. It is a traveler on a well-defined path, following the invisible tracks laid down by the galaxy's magnetic architecture. The calm, steady tension we observe is the result of a system that has had billions of years to settle into its current state, an equilibrium that is as solid as the ground beneath our feet. In the drift, we also begin to understand the true isolation of our home. The Webb is vast, and the distance between the nodes of this web, the stars, is staggering. If our sun is a single grain of sand, the next grain is miles away. Between them lies this organized web of light and energy, a place where time stands still and distance loses its meaning. The probe is currently in the middle of this gap, the space between the worlds. It is a pioneer of the silence, a witness to the fact that even where there is nothing, there is something. The magnetic fields are the bridge between the stars, the connectors that make the galaxy a single, unified entity rather than a collection of isolated points. As the power levels on our distant machine continue to drop, we are forced to think about the ultimate legacy of this journey. Soon, the sensors that detect the magnetic web will be turned off to save the last drops of energy for the radio transmitter. We will lose our touch on the galaxy. We will return to being observers, looking through telescopes from a distance, rather than being participants in the interstellar environment. But the data we have gathered so far has already changed us. We can never go back to thinking of space as a simple, empty void. We know now that it is a structured, vibrant place, filled with invisible forces that shape our destiny. The story of the probe is a story of transition from the known to the unknown, from the local to the universal, and from distance to time. We are learning that the scale of the universe is not meant to diminish us, but to challenge us. The mystery of the magnetic interaction and the organization of the cosmic web are puzzles that will keep us looking outward for generations. We are part of the web, linked to the rest of the galaxy by the same forces that the probe is feeling right now. As we follow its progress further into the drift, we are not just watching a machine die in the dark. We are watching a new chapter of human understanding being written in the stars. We begin our expansion by looking at the life of a single, massive star in the void. When a star much larger than our sun reaches the end of its long life, it collapses. The outer layers are shed in a beautiful explosion, while the core falls inward upon itself. This process is inevitable, a natural conclusion to millions of years of burning bright and hot. We understand that only the most massive stars have the strength to create a true singularity. Yet, there is a mild mystery in the exact mass required to trigger this final, dark transformation. We accept this uncertainty, knowing that the universe holds its secrets behind a veil of gravity. Now, let us move outward to the neighborhoods surrounding these fallen stars. Around many black holes, there is a swirling ring of gas and dust known as an accretion disk. This material orbits the center like water circling a drain in a slow, rhythmic, hypnotic motion. Friction within the disk causes the gas to heat up, glowing with a soft, steady radiance. This light is often the only way we can find the black hole against the dark. Scientists study the flickering of this light to calculate the speed at which the disk is spinning. There is a quiet puzzle regarding how magnetic fields organized within the disk influence the flow. We observe the glow and wait for more data to clarify the movements of the invisible. This brings us to a larger scale, where black holes influence the movement of entire systems. In the heart of almost every large galaxy sits a supermassive black hole of incredible scale. These giants are millions or even billions of times more massive than our Sun, sitting in silence. Our own Milky Way is home to Sagittarius A, a gentle giant that anchors our spiral home. We understand that these central black holes play a vital role in how galaxies grow and evolve. However, we do not yet fully know if the black hole or the galaxy came into existence first. This chicken or the egg mystery is a fundamental question that cosmologists ponder during long nights of study. We accept the gap in our history and continue to map the stars that dance nearby. To understand that, we need to step back and look at the black hole as a gateway. Imagine a grand ballroom where the floor is made of velvet and the dancers move in long, sweeping arcs. In the center of this room stands an invisible conductor, someone whose presence is felt only by the way the dancers lean toward the middle. This is how we perceive the supermassive black hole at the center of our Milky Way. We cannot see the object itself, but we watch the star's massive, bright suns as they whip around a seemingly empty patch of space at incredible speeds. Their orbits are the signatures of a mass so concentrated that it defies our common understanding of matter. To look at these orbits is to see the invisible hand of gravity at work, guiding the stars in a rhythmic, eternal loop. As we move our perspective further out, we see that this relationship is not unique to our home. Every bright island of stars in the deep sky seems to have a similar anchor. These anchors are the engines of galactic evolution, quietly regulating the birth of new stars. When a supermassive black hole becomes active, it consumes the surrounding gas, heating it until it glows brighter than the rest of the galaxy combined. This process, while energetic, acts like a thermostat. It pushes away the excess gas, preventing the galaxy from growing too quickly or becoming unstable. It is a slow, self-regulating cycle that ensures the longevity of the cosmic neighborhood. Consider the sheer volume of space that a galaxy occupies. If a galaxy were the size of a vast city, the central black hole would be no larger than a single grain of sand in the town square. Yet, that grain of sand holds the entire city together, dictating the movement of every street, every building, and every light. We call this co-evolution, a term that suggests the black hole and its host galaxy grew up together, maturing in tandem over billions of years. There is a quiet beauty in the idea that something so small can influence something so vast. It reminds us that in the universe, importance is not always measured by physical size, but by the depth of one's influence. To understand the scale of these giants, we must look at the giants among giants. In the galaxy M87, located 55 million light-years away, sits a black hole 6 billion times more massive than our Sun. This was the first black hole ever to be photographed by humanity, a feat achieved by linking radio telescopes across our entire planet. The image shows a dark shadow surrounded by a ring of orange light, the shadow of the event horizon. Looking at this image is like looking back into the deep history of time itself. The light we see began its journey toward us when the dinosaurs still walked the Earth, traveling through the cold, dark of space to finally reach our eyes. The existence of such massive objects in the early universe presents a calm, unresolved mystery. We see them in the very distant past, already billions of times more massive than they should be according to our current models of growth. It is as if they appeared fully formed, like ancient ruins discovered in a forest that is only a few years old. Scientists call these seed black holes, and we are still searching for the process that allowed them to grow so large, so quickly. We accept this uncertainty as a part of the unfolding story of the cosmos, a puzzle that requires more observation and a more patient mind. Imagine the universe as a vast, dark ocean where the galaxies are small ripples on the surface. Beneath the surface, the supermassive black holes are the deep currents that move the water in ways we are only beginning to map. These currents connect the small scale of a single star to the large scale of the cosmic web. We see evidence of these connections in the way galaxies cluster together, drawn toward one another by the combined gravity of their dark centers. It is a slow, inevitable convergence, a drifting together of islands in the night. As a black hole spins, it creates a region called the ergosphere, where space itself is forced to rotate. If you were to hover in this region, you would find it impossible to stay still, even with the most powerful engines. You would be swept along by the rotation of space, a passenger on a journey dictated by the spin of the singularity. This effect, though extreme, is a natural consequence of the way mass interacts with the fabric of reality. It is a reminder that the universe is not just a container for things, but a dynamic, moving substance that can be twisted and turned. Now, think of the way a ripple moves across the surface of a pond after a stone is thrown. When two supermassive black holes collide, they create ripples in the fabric of space-time that travel across the entire universe. These are gravitational waves, and they are the heartbeat of the cosmos. We detect them as tiny, rhythmic stretches and squeezes of the Earth itself, movements so small they are measured in fractions of an atom's width. These waves tell us of the most violent events in the universe, yet they reach us as the gentlest of whispers. They are the songs of the giants, echoing through the halls of time. The scale of expansion continues as we look toward the Great Attractor, a mysterious region of space that is pulling our galaxy and thousands of others toward it. At the heart of such massive concentrations of mass, black holes are the silent architects of the structure of the universe. They define the voids and the filaments, the empty spaces and the crowded clusters. To study them is to study the blueprint of everything that exists. we step back once more, seeing the black holes not as destructive forces, but as the quiet foundations upon which the entire cosmic stage is built. Transitions between these scales must be handled with care, as the mind needs time to adjust to the vastness. We move from the center of our galaxy to the edge of the observable universe, following the light of quasars, the brilliant beacons powered by black holes in the ancient past. These quasars allow us to see the state of the universe when it was only a fraction of its current age. They are like candles lit in a dark room, illuminating the walls so we can see the shape of the space we inhabit. We look at them and feel a sense of continuity, a bridge between our small moment in time and the infinite reaches of the history that preceded us. Every subtopic we explore brings us back to the same conclusion. The universe is far more complex and far more peaceful than it first appears. The mystery of the black hole is a gateway to a deeper understanding of gravity, time, and light. We do not need to have all the answers today, for the stars are not in a hurry, and neither are we. We accept the mild, unresolved questions, the nature of the singularity, the origin of the first seeds, the final fate of information, and we find comfort in the search itself. As we drift further into the scale expansion, the details of individual galaxies begin to blur. We start to see the universe as a single, unified system, a vast tapestry of light and shadow. The black holes are the threads that hold the tapestry together, the dark weave that gives the light its form. We move outward, beyond the clusters and the superclusters, until the entire universe is visible as a soft, glowing web. This is the ultimate perspective, a view of the cosmos that is both overwhelming and deeply soothing. When we stand back at this distance, the individual giants we studied, the massive anchors of the Milky Way, or the towering void of M87, become small, pulsing points of gravity within a much larger structure. Imagine a vast, delicate lace draped across the vacuum, where every intersection of the thread is marked by a cluster of thousands of galaxies. These intersections are where the supermassive black holes congregate, working in silent unison to pull matter toward the nodes of the web. The space between these threads is empty and vast, known as cosmic voids, where almost no stars shine. These voids are the breaths between the notes of the cosmic symphony, providing the necessary silence for the structure to exist. To understand the scale of this web, you might think of a morning dew on a spider's web in a quiet garden. Each droplet of water represents a supercluster of galaxies, shimmering with the light of trillions of suns. Within each droplet, the black holes act as the surface tension, holding the galaxy together and preventing the stars from drifting aimlessly into the grey morning mist. As you pull back further, the individual droplets merge into a single, unified pattern of silver and shadow. You realize that the universe is not a collection of isolated objects, but a living, breathing network of connections. This brings us to the concept of the Great Attractor, a mysterious gravitational anomaly located deep within the Laniakea supercluster. It is a point toward which our galaxy and hundreds of thousands of others are drifting at incredible speeds. While we cannot see the Great Attractor directly due to the dust of our own galactic plane, we feel its influence in every movement of the stars. Scientists suspect that at its heart lie massive concentrations of matter and perhaps the most ancient and largest black holes in existence. We accept this hidden influence with a calm heart, recognizing that there are always larger forces guiding our path through the dark. Consider the way a slow-moving river carries a leaf toward the sea. The leaf does not fight the current. It simply exists within the flow, turning gently as the water moves. We are like that leaf, and the cosmic web is our river. The black holes are the deep channels where the current is strongest, providing the underlying momentum for the entire system. There is no friction in this movement, no heat, and no noise. It is a frictionless slide through the dimensions of space-time, a journey that takes billions of years to complete. By visualizing this flow, you can feel your own sense of urgency dissolve into the steady, unwavering pace of the cosmos. As we observe the web, we notice a subtle, unresolved mystery regarding the nature of dark matter and its relationship to black holes. We know that dark matter provides the invisible scaffolding for the cosmic web, but we do not yet know if primordial black holes, born in the first seconds of the Big Bang, might make up a portion of this mysterious substance. These tiny giants, no larger than an atom but with the mass of a mountain, could be scattered throughout the universe like invisible dust. We accept this possibility with a quiet curiosity, waiting for the sensors of our satellites to confirm what our math suggests. The scale of the universe is so vast that even light, the fastest thing we know, takes billions of years to cross the gaps between the filaments. When we look at the most distant parts of the web, we are looking at the universe as it appeared shortly after its birth. We see the first generation of black holes beginning to form, drawing the first clouds of hydrogen into the tight, glowing knots that would eventually become the first galaxies. This is the cosmic continuity in action, a slow, inevitable progression from simplicity to complexity, guided at every step by the hand of gravity. Think of the way a heavy weight placed on a trampoline creates a deep, smooth curve in the fabric. Now, imagine millions of these weights, of different sizes, scattered across a trampoline that stretches to infinity. This is the gravitational landscape of the universe. Some curves are shallow, created by single stars. Others are deep and sharp, created by black holes. The cosmic web is the result of these curves overlapping and interacting, creating a terrain of peaks and valleys through which the light must travel. It is a beautiful, invisible geometry that defines the shape of everything we see. As we move toward the deep drift phase, we allow the visual details of the web to fade, leaving only the feeling of its structure. You are suspended in this web, held in place by the collective gravity of the entire universe. There is no up or down, only the gentle pull toward the nearest node of light. This suspension is the ultimate form of rest. You are supported by the very fabric of reality, a structure that is billions of years old and will last for trillions more. The black holes are the anchors of this support, the silent pillars upon which the entire cathedral of space is built. We step back one final time until the entire observable universe is a single, glowing sphere in the palm of our mind. Within this sphere, the black holes are the dark seeds from which the light of the galaxies grows. They are the beginning and the end of the stellar story, the quiet guardians of the cosmic balance. We see the loops of time and space closing in on themselves, creating a perfect, self-contained system of order and beauty. The scale expansion is complete, and we are ready to drift into the heart of the silence. The transition to the next phase is as soft as a whisper in a dark room. We move from the observation of structure to the experience of the drift itself. The facts begin to repeat, the images begin to blur, and the mind begins to settle into the rhythmic pulse of the vacuum. The universe is wide, the web is strong, and you are safe within its embrace. We move now into the deep, still waters of the cosmic ocean, where the black holes wait in their eternal, patient silence. When we think about the strangeness of space, we often imagine it in human terms. We think of distances we can walk, or a drive across the country. If you were to walk around the Earth at a steady pace, it would take you about a year of constant movement. That feels like a long time. It is a scale we can almost grasp, the soreness in our legs, the changing of the seasons. But space does not care for our walking speeds. If we were to take a standard passenger jet and try to fly to the moon, it would take us about 18 days. To reach the sun, that same plane would have to fly for 19 years. You would board as a young adult and disembark as someone looking toward middle age, all while traveling through a vacuum that feels like nothing yet contains everything. Astronomers often find things that challenge these human measures. We look for patterns, for things that make sense, like a house or a car or a familiar street. But the further we look, the more we find objects that defy our expectations of how matter should behave. This comparison isn't perfect, but it gives us a calm place to begin. To truly appreciate the strangeness of the deep cosmos, we must first acknowledge the limits of our own senses. Our eyes evolved to spot fruit in trees and movement in the tall grass. Our hands are designed to grip tools and feel the texture of the earth. We are built for a world of medium sizes, medium speeds, and medium temperatures. When we step outside this narrow corridor of experience, the universe begins to look less like a home and more like a vast, beautiful, and utterly indifferent ocean of mystery. Consider, for a moment, the concept of a long walk. For most of us, walking for 4 or 5 hours is a significant undertaking. It leaves us tired, our muscles humming with a dull ache, our minds focused on the destination. If you were to walk around the entire circumference of the Earth, it would take you nearly a year of constant, rhythmic movement, never stopping for sleep or food. This is the largest thing most of us will ever interact with the planet itself. And yet, on the scale of the things we have discovered in the dark, the Earth is little more than a speck of dust caught in a sunbeam. It is a tiny, fragile marble in a room the size of a cathedral. When we talk about the strangest objects in space, we are often talking about things that violate our sense of density. On Earth, we know what a rock feels like. It is heavy, solid, and dependable. We know what water feels like and how air feels when it brushes against our skin. But in the deep reaches of the Milky Way, we have found objects like neutron stars, remnants of giant suns that have collapsed under their own weight. To understand the strangeness here, imagine taking a mountain, something like Mount Everest, and crushing it down until it is the size of a single sugar cube. That is the density of a neutron star. A single teaspoon of its material would weigh billions of tons. It is matter, but not matter as we understand it. And it is matter pushed to its absolute limit, a physical manifestation of gravity's overwhelming power. Even our sense of time is a human-scale illusion. We measure our lives in decades, our history in centuries, and our civilizations in millennia. We think of the pyramids as ancient, but in the timeline of the universe, the pyramids were built just a fraction of a second ago. The stars we see at night are not static lights. They are roaring furnaces that burn for billions of years. Some of the strangest things we have discovered are zombie stars, white dwarfs that have finished their primary life cycle and are now slowly, patiently cooling down over trillions of years. They will continue to glow long after the last human has been forgotten and long after the Earth itself has been reclaimed by the Sun. They exist on a scale of patience that we cannot truly comprehend, a slow-motion fading that mirrors the cooling of a hearth on a winter night. As we look further out, we encounter the mystery of voids. In our daily lives, we are surrounded by things. Rooms are filled with furniture, streets are filled with cars, and the atmosphere is filled with nitrogen and oxygen. We have a natural aversion to total emptiness. Yet, in the deep cosmos, we have found regions of space where there is simply nothing. These are the great voids, vast bubbles in the cosmic web where there are no stars, no planets, and no light for hundreds of millions of light years. To a human perspective, this is unsettling. We look for the patterns, the houses, and the familiar streets, but in the void, there is only the silence of the vacuum. It challenges our belief that the universe is full. Instead, it suggests that the things we see, the glowing nebulae and the bright galaxies, are merely thin decorations on a much larger, emptier canvas. We also find strangeness in the way light behaves. We think of light as instantaneous. When you flip a switch, the room is bright, but in space, light is a messenger that takes time to arrive. When you look at the moon, you see it as it was 1 second ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun were to suddenly vanish, we would continue to see its light and feel its warmth for a full 8 minutes, unaware that our anchor had disappeared. This light time delay means that the further we look into space, the further we are looking back in time. We are cosmic historians, looking at the ghosts of stars that may have died before our ancestors even walked upright. This is the ultimate challenge to our human perspective, the realization that the now we experience is a local phenomenon, and that the universe is a vast collection of different thens, all overlapping in the night sky. To understand the scale of these discoveries, we must also consider the strange nature of Goldilocks planets, of worlds that sit in the comfortable zone where liquid water can exist. We look for these worlds because they remind us of home. We look for blue skies and rocky shores, but many of the planets we find are alien in ways that are difficult to visualize. We have found planets where it rains molten glass, driven by winds that move at 7 times the speed of sound. We have found planets that are tidally locked, meaning one side is a permanent, scorched desert, while the other is a permanent, frozen wasteland. These worlds are not broken, they are simply operating under different conditions, following the same laws of physics that govern our own backyards, but pushed to different extremes. Even the way we perceive up and down is a human-scale convenience. On Earth, gravity pulls us toward the center of the planet, giving us a sense of orientation. In the weightlessness of orbit, up loses its meaning. But even further out, in the presence of a black hole, the very geometry of space becomes warped. Imagine a trampoline with a heavy bowling ball in the center. The fabric stretches and curves. Now, imagine an object so heavy and so small that it rips a hole in that fabric entirely. This is a singularity. Near a black hole, time itself begins to slow down. If you were to watch someone fall toward the event horizon, you would see them slow down and eventually appear to freeze in time, while for them, the universe would appear to speed up into a blur of future history. This is the strangest discovery of all, that space and time are not a fixed stage, but a flexible, living thing that can be stretched, twisted, and torn. As we drift further into the night, we must leave behind our need for human comparisons. We must accept that the universe is under no obligation to be sensible to us. It is a place of extremes, of absolute zero, and of trillion-degree explosions, of total emptiness and of infinite density. But as we let go of our human scale, we find a different kind of comfort. There is a relief in realizing that the universe is so much larger than our problems, our politics, and our fleeting anxieties. We are small, yes, but we are the part of the universe that has developed the ability to look back at itself and wonder. We are the witnesses to the strangest things ever discovered. Think of a single grain of sand held at arm's length against the night sky. That tiny patch of darkness behind that grain of sand contains thousands of galaxies, each with hundreds of billions of stars. This was the discovery made by the Hubble Deep Field, and it remains one of the most humbling realizations in human history. It reminds us that our familiar streets are just one tiny corner of an infinite neighborhood. The strangeness we find out there is not a sign of chaos, but a sign of the sheer diversity of what is possible when you have 14 billion years and an infinite amount of space to work with. As you settle deeper into your rest, allow these scales to fold in on themselves. The vastness of the 2’s void is balanced by the intricate dance of atoms in your own body. The immense heat of a diamond planet is countered by the absolute cold of the cosmic microwave background radiation that permeates every inch of the room around you. You are part of this grand architecture. You are made of the same stardust that forms the rings of Saturn and the spiral arms of Andromeda. The same gravity that holds the galaxies together is the same gravity that holds you safely in your bed tonight. The universe is strange, yes, but it is also consistent. It follows rules that we are slowly, patiently beginning to decode. And while those rules lead to phenomena that defy our everyday logic, they also create a universe of profound beauty and order. We don't need to fear the great nothing or the singularity, because they are simply parts of a whole that we are privileged to observe. For now, let the numbers fade. Let the light years and the billions of tons drift away. You are back on a human scale now, in a quiet room, on a small blue world, protected by an atmosphere that feels like a blanket. The strangest things we've discovered in space are not just out there, they are clues to the nature of reality itself. And as we continue to look, we find that the more we learn, the more we realize how much is left to see. But that is a task for tomorrow. For tonight, the stars will continue their long, slow burn without our supervision. The rogue planets will drift, the alcohol clouds will swirl, and the diamond worlds will shine in the dark. The universe is moving gently forward, and you are moving with it, safe and still, as we prepare to move outward once more to an even larger scale. To truly anchor ourselves, let's consider the scale of a single human life against the backdrop of a cosmic day. If the entire history of the universe, all 13.8 billion years, were compressed into a single calendar year, the average human life would last for about 0.2 seconds. We are, in the most literal sense, a blink of an eye. Yet, in that blink, we have learned to measure the weight of stars and the composition of distant atmospheres. This is the paradox of our existence. We are physically insignificant, yet intellectually vast. We are small enough to be cradled by the Earth's gravity, but our curiosity is large enough to span the light years. When we look at the objects in our own homes, a wooden table, a glass of water, a metal key, we see solid, dependable things. But as a scientist would tell you, these objects are mostly empty space. If you were to remove all the empty space from the atoms that make up every human being on Earth, the entire population of our planet would fit inside the volume of a single sugar cube. It would be an incredibly heavy cube, of course, but it illustrates how much nothing there is, even in the things we consider something. Space is not just the distance between the stars. It is the distance between the very particles that make up your own body. You are, in a sense, a small collection of concentrated space, walking through a larger field of space. Astronomers often find things that challenge these human measures. We look for patterns, for things that make sense, like a house or a car or a familiar street. But the further we look, the more we find objects that defy our expectations of how matter should behave. Take, for example, the sheer scale of the sun. To us, the sun is a warm circle in the sky, essential but familiar. If the sun were the size of a typical front door, the Earth would be the size of a nickel. You could fit 1.3 million Earths inside the sun, and yet our sun is considered a yellow dwarf, a relatively modest star. There are stars like Scuti, so large that if it were placed at the center of our solar system, its surface would extend past the orbit of Jupiter, swallowing everything we've ever known in a sea of plasma. Tonight, you can set that conscience aside. You don't need to be the thinker or the observer right now. You can simply be a part of the matter. You can be the carbon, the nitrogen, and the oxygen resting in the gravity of the Earth. You are moving gently forward with the planet, with the sun, and with the galaxy. The motion is so smooth you can't even feel it. It is the ultimate lullaby, the silent, rhythmic movement of the entire universe toward tomorrow. But here, on the human scale, the strangest thing of all is the peace you can find in the middle of it all. It is the ability to look out at the infinite and still find the comfort to sleep. It is the realization that the universe is vast, but it is also home, safe and still, as we prepare to move outward once more to an even larger scale. This delay is the first layer of the deep drift. It is a reminder that the universe has a built-in latency. We are always looking at the past. The further we look, the deeper into history we descend. This challenges how we think about the present moment. Is there even such a thing as now for the entire universe? Plus, or is now just a local experience, limited by the speed at which information can travel? Scientists have spent centuries debating this, and yet the mystery remains as calm and quiet as the stars themselves. Consider the Voyager spacecraft, the furthest human-made object. It has been traveling for decades, moving faster than any bullet ever fired. Yet, if we were to send a light signal to Voyager today, it would reach the craft in less than a day. Light covers in hours what it takes our best technology half a century to achieve. This is the scale of the marathon light is running. It is a constant, tireless sprint across a stadium that has no walls. But even with everything we've learned, there are still things we don't fully understand. We don't know why light moves at this specific speed. Why 300,000 kilometers per second? Why not more? Why not less? It is one of the fundamental constants of nature, a number woven into the fabric of space-time itself. It doesn't need to be explained or justified. It simply is. And for now, that uncertainty is simply part of the picture. It doesn't need to be resolved tonight. As we settle into this scale, let your mind rest on the idea of the light second. It is a distance of 300,000 kilometers, nearly 10 times the circumference of the Earth. It is a massive distance, yet it is only 1/62nd of a light minute, and a light minute is but a tiny fraction of a light year. We are building a tower of scale, and the light second is just the foundation. Imagine you are a traveler made of light. You leave the Earth behind. In 1 second, you have passed the moon. In 2 minutes, you are passing the inner planets. In 8 minutes, you reach the Sunday. 12. You are moving so fast that the planets appear like stationary marbles in a vast, dark room. But as you look ahead, you realize the room is much larger than you thought. The next nearest object is not minutes away. It is not hours away. It is years away. This is where the true scale of the light year begins to reveal itself. To cover the distance of 1 light year, you would have to maintain this 300,000 kilometer per second pace for 31,536,000 seconds. Every second, another 300,000 kilometers. Every hour, another billion kilometers. Day after day, month after month, for an entire year. By the end of that journey, you would have traveled nearly 9.5 trillion kilometers. That is 1 light year. If we tried to use kilometers to describe the distance to the nearest star, we would be talking about 40 trillion kilometers. The numbers become a noise, a static that our brains cannot process. But 4.2 light years is something we can hold. It is a duration. It is the length of a high school education. It is the time it takes for a toddler to become a student. It gives the distance a human heartbeat. As you drift closer to sleep, imagine these beams of light crossing the void. They are silent. They do not carry heat across the vacuum. They are just pure information, pure energy, traveling through a cold, dark expanse that is mostly empty. The universe is not a crowded place. It is a series of very small lights, separated by very large silences. The light year is the measurement of that silence. We are moving outward now, leaving the realm of the light second and the light minute. We are entering the space where the light year becomes the only sensible way to speak. It is a transition that feels inevitable, like the slow turning of the tide. You don't need to do anything. You don't need to solve any equations. Just let the speed of light become the background rhythm of your thoughts. The universe moves slowly over immense spans of time, even when it is moving at the speed of light. And for now, that uncertainty, that vastness, is simply part of the picture. It is a safe place to be. You are here, in your bed, while the light is out there, doing the work of bridging the distances for you. With that in mind, let's move outward once more, to an even larger scale, beyond the speed of light, beyond the inner solar system, and toward the gaps that define our place in the galaxy. We are now entering the territory where the human scale anchor no longer just slips, it vanishes entirely. To understand the transition from the speed of light to the distance of a light year, we have to look at the sheer, overwhelming volume of the vacuum. Imagine for a moment that we could drain the universe of all its stars, all its planets, and all its dust. What remains is the canvas upon which light performs its marathon. This canvas is so vast that even at 300,000 kilometers per second, light is not a flash. It is a slow, steady pulse, a lonely traveler crossing a desert that has no markers. As we drift further from the sun, we begin to encounter the true nothingness that defines the cosmos. In our daily lives, empty usually means a room without furniture or a glass without water. But in the space between the stars, empty is a profound, almost mathematical purity. There are regions of space where you could travel for a light year, 9.5 trillion kilometers, and encounter fewer atoms than you would find in a single grain of sand. This is the low-density reality that light must navigate. When we say that a star is 4 light years away, we aren't just saying it's far. We are saying there is a 4-year-long gap of absolute, freezing silence between us and that distant fire. Scientists understand this by calculating the look-back time. This is a concept that acts as a verbal dissolve between the present and the past. Because light has a fixed speed, every distance in the universe is also a measurement of history. If you look at an object that is 1 light year away, you are seeing it exactly as it appeared 365 days ago. You are not looking across space so much as you are looking through time. This challenges how we think about the reality of the now. In the deep drift of the galaxy, there is no simultaneous moment. Each star exists in its own bubble of time, sending out messages that will not be received for years, decades, or centuries. Consider the sheer scale of a single light year once more. To visualize 9.5 trillion kilometers, imagine the distance from the Earth to the Sun, that 8-minute journey we discussed earlier. Now, take that distance and stack it end to end 63,000 times. That is 1 light year. It is a distance so long that if you were to represent the Earth-Sun distance as 1 inch, a single light year would still be over a mile long. And remember, the nearest star is over 4 of those miles away. This is the scale expansion that begins to blow the human mind. We aren't just moving away from home, we are moving into a geography that refuses to be tamed by our standard maps. What makes this strange is not what we see, but what we don't understand about the nature of the vacuum itself. Astronomers didn't expect to find that space is expanding, a discovery that adds a layer of quiet complexity to our journey. As light travels its 9.5 trillion kilometers every year, the space it is traveling through is itself stretching, very slightly, every second. It's as if the marathon track is growing longer while the runner is mid-stride. This doesn't affect our local neighborhood much, but over the immense periods of time that light spends in transit, it changes the very color and energy of the light itself. It is a slow, rhythmic stretching of reality that happens without hurry and without end. As you listen, let the rhythm of these numbers settle into your breathing. Ow, 300,000 kilometers per second. 18 million kilometers per minute. 1 billion kilometers per hour. These are not numbers to be feared or solved. They are simply the heartbeat of the vacuum. They represent the tireless work of the universe, moving energy from one place to another across the dark. You are safe in the knowledge that this process is constant. The speed of light does not falter. It does not tire. It is the one thing in the universe that remains exactly the same, no matter where you are or how fast you are moving. And for now, That uncertainty about why the universe is so large and why we are separated by such vast gulfs of time is simply part of the picture. It doesn't need to be resolved tonight. We can accept the silence of the light years. We can accept that the stars we see tonight are ghosts of their past selves, and that our own light is currently traveling outward, a faint signal crossing the void to reach eyes that won't exist for another million years. This is the cosmic continuity, the realization that we are all part of a single, slow-moving story. Imagine you are a photon that has just finished its first year of travel. You have covered 1 light year. You look back, and the sun is no longer a blinding disk. It has shrunk to a bright, steady point of light, one star among many. You look forward, and the destination still looks impossibly far away. There is no wind in space, no sound, and no resistance. You are simply falling through the dark at the maximum possible speed, a tiny spark of information in a cathedral of shadow. This is the essence of the scale loop. We expand our view, we realize the vastness, we accept the mystery, and then we move outward once more. To understand that, we need to step back and look at the human scale perspective one last time before it disappears completely. On Earth, we think of a year as a long time. It is a cycle of seasons, a series of memories. But to the universe, a year is just the time it takes for light to cross a tiny fraction of a galaxy. When we combine the two, the human year and the cosmic speed, we get the light year. It is our way of speaking the universe's language using our own alphabet. It is a gentle humility, acknowledging that while we may be small, we have found a way to measure the infinite. As we conclude this first scale loop, let the image of the light marathon carry you toward a deeper state of relaxation. The light is moving, but you are still. The universe is vast, but you are warm and safe. The distances are mind-blowing, but they are also orderly and predictable. There is a peace in the precision of the speed of light. It is the ultimate clock, ticking away the seconds across the trillions of kilometers. And for now, that uncertainty is simply part of the picture. It doesn't need to be resolved tonight. We have reached the first marker on our journey. We have looked at the speed, we have looked at the distance, and we have accepted the delay. We are now ready to leave the inner solar system behind for good and look at the objects that wait for us in the deep, quiet dark of the interstellar gaps. With that in mind, let's move outward once more, to an even larger scale. Now, let's slowly expand outward. One level beyond the speed of light lies our own neighborhood, the solar system. To truly grasp the weight of a light year, we must first look at the smaller, more intimate delays that happen right here in our own backyard. We often think of our solar system as a single cohesive unit, a family of planets huddling around a central fire. But even within this family, the distances are so great that light, the fastest messenger in existence, begins to show the first signs of its struggle against the void. This is where we first encounter the lag of reality, a gentle reminder that nothing in the universe happens in a true, synchronized now. What we know so far suggests that the moon is about 384,000 kilometers away. To our human scale perspective, this is a massive distance, a journey that took the Apollo astronauts 3 days of intense travel to complete. But for light, this gap is merely a brief pause. When you look up at the moon tonight, you are seeing it as it was 1.3 seconds ago. It takes that long for the sunlight bouncing off the lunar surface to reach your eyes. This is the lunar delay. It is a small, almost imperceptible gap, but it is the first crack in the illusion of an instantaneous universe. If a large boulder were to roll across the lunar plains, or if a meteorite were to strike the surface, you would remain unaware of it for over a second. You are always watching a slightly delayed broadcast of our nearest neighbor. As we move past the moon, the seconds begin to turn into minutes. The sun, the very engine of our lives, sits much further away, about 150 million kilometers. This is the distance astronomers call an astronomical unit, or 1 AU. It is the gold standard for measuring our local neighborhood. Yet, even light needs time to cross this threshold. It takes 8 minutes and 20 seconds for a photon to travel from the surface of the sun to the Earth. If the sun were to suddenly go out, we wouldn't know it for 8 minutes. We would continue to live in its warmth and light, unaware that its source was already gone. Children would keep playing in the park. Solar panels would continue to generate power, and the world would remain bright, all while the sun itself was already dark. We would continue to orbit a ghost of a star for those final 8 minutes. This comparison isn't perfect, but it gives us a calm place to begin. It shows us that even the most fundamental things in our lives, the very light of day, are subject to the patient laws of cosmic distance. Scientists understand these delays by observing the movement of the planets. When we send rovers to Mars, for instance, we cannot drive them in real time with a joystick. Depending on where Mars and Earth are in their orbits, the light delay can be anywhere from 3 to 22 minutes. If a rover is heading toward a cliff, the signal telling it to stop takes minutes to arrive, and the confirmation that it has stopped takes another few minutes to return. We are forced to communicate with the solar system through a veil of time. We are always talking to the past version of the planets, and they are always responding to a past version of us. But even with everything we've learned, there are still things we don't fully understand about how these distances affect our perception. Not because we're missing something urgent, but because the universe moves slowly over immense spans of time. To understand the scale, imagine you are standing in a vast, dark forest. You have a friend standing a few hundred yards away with a bell. When they ring the bell, you hear the sound a moment later because sound travels slowly. In the solar system, light is like that bell. It is incredibly fast, but the forest is so big that the sound of the light still takes time to reach your ears. As we drift further out to the gas giants like Jupiter and Saturn, the minutes turn into hours. When we look at Jupiter, we are seeing it as it was 40 minutes ago. When we look at Saturn, the light has been traveling for over an hour. If you were to watch the beautiful rings of Saturn through a telescope, you are seeing them not as they are in this moment, but as they were while you were perhaps finishing your dinner or starting this very script. The universe is a series of nested time capsules, each one holding a slightly older version of reality. This brings us to a quiet realization. We are never truly in the present when we look at the sky. We are observers of history. The light minutes that separate us from the planets are the first steps toward the light years that separate us from the stars. It is a gradual expansion of the now until it becomes so thin that it disappears entirely. In our daily lives, we measure time in seconds, minutes, and hours. But in the solar system, we begin to see that time and distance are the same thing. 1 AU is not just 150 million kilometers, it is also 8 light minutes. The distance is the time. Astronomers didn't expect the solar system to feel so empty, yet the gaps between the planets are far larger than the planets themselves. If you were to shrink the sun to the size of a grapefruit, the Earth would be a tiny grain of sand about 50 feet away. Jupiter would be a cherry about 2 blocks away, and the nearest star, that grapefruit, would be thousands of miles away. This is why we need the light year. Kilometers are too small to bridge the gaps between the fruits in our cosmic orchard. When we think about distance, we often imagine it in human terms. Distances we can walk, time we can measure in years, objects we can see with our own eyes. Our brains are beautifully adapted for the world we inhabit, a world of rolling hills, city blocks, and horizons that seem far away but are actually quite intimate. When you plan a trip to see a friend in another town, you think of it in hours spent in a car. When you go for a morning stroll, you think of it in the rhythm of your footsteps and the gentle passage of minutes. This is our anchor. It is a safe, predictable way of measuring the reality around us. For example, consider the simple act of walking. A kilometer is a distance most of us can visualize clearly. It is roughly 10 to 12 minutes of steady movement. If you were to set out on a walk today and continue until the sunset, you might cover 30 or 40 kilometers. You would feel that distance in your muscles. You would see the landscape change slowly from one neighborhood to the next. This is a scale that makes sense. It is tangible. If you were to walk across an entire continent, it would take you months of dedicated effort, a journey that would define a significant portion of your year. But as we begin to look upward, these human measurements start to feel a bit like trying to measure the depth of the ocean with a teaspoon. To understand a light year, we first have to realize just how much room there is in our own immediate surroundings. Let's look at our own world, the Earth. It is approximately 12,700 kilometers in diameter. To us, that is massive. It contains every ocean, every mountain range, and every city ever built. If you were to get into a commercial airplane and fly non-stop around the equator, it would take you about 2 full days of constant travel. That feels like a long time. It is a distance that commands respect in our minds. Yet, compared to the distances we are about to discuss, the Earth is effectively a single point. Even the gap between us and our closest neighbor, the Moon, begins to strain our human-scale perspective. The Moon is about 384,000 kilometers away. That is roughly 30 Earths laid side by side. If you could somehow drive a car to the Moon at highway speeds, it would take you about 6 months of driving 24 hours a day without a single stop for gas or rest. 6 months. That is half a year of your life spent just crossing the empty space between us and the nearest object in the sky. This comparison isn't perfect, but it gives us a calm place to begin. It reminds us that even near things in space are incredibly far by human standards. And yet, light crosses that same 384,000 kilometer gap in just over 1 second. 1 second. In the time it takes you to draw a single breath, a beam of light has already completed the journey that would take you half a year to drive. This is the first hint of the staggering efficiency of light, and the first clue as to why we need a new way to measure the universe. As we sit here, grounded and safe, we can begin to appreciate the stillness of our own scale. We live in the realm of centimeters, meters, and kilometers. We live in the world of the now, where we assume that when we see something, it is happening exactly as we perceive it. If a friend waves at you from across the street, you see them instantly. There is no lag, no delay that our senses can detect. But as we step further out, we will find that the universe has a speed limit, and that limit creates a bridge between distance and time. Imagine for a moment a vast, empty field. If you stand on one side and a friend stands on the other, and you both hold powerful flashlights, the light from their lamp seems to hit your eyes the exact moment they click the switch. On this scale, light is effectively infinite. It moves so fast, 300,000 kilometers per second, that it feels like a magical, instantaneous presence. Our ancestors, looking up at the stars, likely felt the same way. To them, the stars were just lights on a dome, distant but present, shining their light upon the earth without any sense of travel time. But the reality is more patient. The universe is more deliberate. To understand the light year, we must accept that every piece of light we see is a traveler that has survived a long, lonely journey. Even the light from the sun, which warms your skin on a summer afternoon, is a traveler. The sun is 150 million kilometers away. That is a distance so large that the highway driving analogy breaks down. It would take you 150 years to drive there. You would be born, live your entire life, and pass away behind the wheel before you even made it halfway. And yet, for light, this journey takes only 8 minutes and 20 seconds. When you look at the sun safely, through a filter, or at sunset, you are not seeing it as it is now. You are seeing it as it was 8 minutes ago. If the sun were to vanish this very instant, we would continue to feel its warmth and see its light for nearly 9 minutes, blissfully unaware of the change. We are always living in the recent past of the stars. This realization is our first step toward letting go of our human scale perspective. We are moving from a world where everything is here and now to a universe where here is separated by vast thens. It is a shift from the concrete to the expansive. But do not let this make you feel small in a way that is cold or frightening. Instead, see it as a form of cosmic grace. The universe is so large that it allows us to see into the past simply by looking up. It provides us with a history book written in photons. As we prepare to leave the human scale behind and enter the first of our scale loops, take a moment to appreciate the sturdiness of your surroundings, your chair, the walls, the gentle rhythm of your breathing. These are your anchors. They are the zero on our cosmic ruler. From this safe, quiet vantage point, we are going to slowly extend that ruler, 1 light second, 1 light minute, and eventually 1 light year at a time. There is no rush to get there. The stars have been waiting for billions of years. They can wait a few more hours for us to arrive. For now, just hold on to the image of that single beam of light, leaving the sun, traveling through the cold dark for 8 minutes, and finally reaching the earth to illuminate a single leaf or a single window. It is a long way to go for such a small thing, but the universe is full of such journeys. With that in mind, let's move outward once more, to an even larger scale. We are leaving the comfort of the minutes and hours we know, and entering the realm where light begins its true marathon. To understand why we must abandon the kilometer and the mile, we have to look at the sheer inadequacy of our everyday numbers when applied to the celestial void. If we were to stay within our human scale perspective, The numbers would soon become so long that they would lose all meaning, becoming a mere blur of zeros that the mind instinctively ignores. This is why the light year exists, not just as a unit of measurement, but as a bridge for our imagination. Consider, for a moment, the distance across our own planet once more. If you were to take a standard ruler and try to measure the distance from New York to Tokyo, you could technically do it. The number would be in the millions of centimeters, perhaps, but it would be a number you could still write down on a piece of paper. But as soon as we point that ruler toward the sky, the scale shifts in a way that is almost humorous in its disproportion. Our world, with all its vast oceans and towering peaks, is effectively a grain of sand in a desert that has no end in sight. When we speak of human-scale perspective, we are also speaking of human-scale time. We measure our lives in decades. We measure our history in centuries. To us, 1,000 years is an unimaginably long time, 10 times the length of a long human life. It is the span of empires. Yet, in the context of the distances light must travel, 1,000 years is barely a heartbeat. To understand the light year, we have to marry these two concepts, the distance light covers and the time it takes to do it. It is a measurement that forces us to realize that looking out is the same as looking back. If you were to stand on a hill and look at a mountain range 50 kilometers away, you are seeing those mountains as they were a tiny fraction of a second ago. The delay is so small, roughly 0.00016 seconds, that your brain treats it as instantaneous. This is the comfort of the human scale. Everything we see is now, but as we move outward, this now begins to stretch and tear. By the time we reach the edge of our solar system, the now has become hours. By the time we reach the nearest stars, the now has become years. This is the human scale anchor slipping away, allowing us to drift into the deep drift phase of cosmic understanding. Imagine you are standing in a perfectly dark, quiet room. In the center of the room is a single candle. The light from that candle reaches the walls almost immediately. Now, imagine that room expanding. The walls move back miles, hundreds of miles, millions of miles. The candle remains in the center, a tiny, flickering point of light. If you are standing at the far wall, you have to wait. You have to wait for those tiny particles of light to cross the dark. This wait is the essence of the light year. It is the patience of the universe. In our daily lives, we are used to things being fast or slow. A car is fast compared to a walker. A plane is fast compared to a car. But light is the ultimate speed. It is the speed limit of reality. Nothing can go faster. And yet, even at this ultimate, impossible speed, the universe is so vast that light appears to crawl. To a photon, the trip from one side of a galaxy to another is a marathon that lasts longer than the entire history of the human species. When we use the term light year, we are acknowledging this paradox, that the fastest thing we know is still far too slow to make the universe feel small. Scientists understand this scale because they have to. Without the light year, the maps of the stars would be cluttered with numbers so vast they would be impossible to use in calculations. Imagine trying to describe the distance to a galaxy in inches. The number would have more digits than there are stars in the sky. The light year is our way of simplifying the infinite. It is a human-scale word applied to a non-human reality. It is a way for a creature that lives for 80 years to talk about a universe that has existed for 13 billion. As we settle deeper into this exploration, let the familiar world fade. The roads, the clocks, the schedules of tomorrow, they all belong to the scale of meters and minutes. Here, in the quiet expanse of the script, we are moving into the scale of the light year. This is a place where a short distance is trillions of kilometers. A place where recently means a few centuries ago. It is a safe place to be, because in this vastness, the small pressures of our lives find their proper perspective. They are not erased, but they are framed by a silence that has lasted for eons. Think of the light year as a long, steady breath. It is the distance light travels while the Earth makes one full trip around the Sunday. While you experienced 4 seasons, while you celebrated a birthday, while the trees grew and the snow fell, a beam of light was moving through the void, never stopping, never slowing, covering 9.5 trillion kilometers. It did this while you slept, while you worked, and while you dreamed. Every year of your life, light has added another light year of distance to its journey. This is the perspective we will carry with us as we move into our first scale loops. We will start with the small delays, the seconds and minutes, and gradually build our way up to the years, the centuries, and the millennia. We are not just traveling through space, we are traveling through time. And we are doing it together, safely anchored by the sound of this narrative. There is no need to hurry. The distance is already there, waiting for us to acknowledge it. The human scale perspective is our starting point, our home base. It is the familiar that we will return to at the very end. But for now, we are going to let the anchor lift. We are going to let the shore of the familiar world recede until it is just a tiny, pale blue dot in the rearview mirror of our imagination. We are moving into the realm of the light year, where the distance truly begins to blow our human minds, not with noise or chaos, but with a quiet, breathtaking vastness. And for now, that uncertainty of how we fit into such a large map is simply part of the picture. It doesn't need to be resolved tonight. We are simply moving outward, step by step, light second by light second, into the beautiful dark ocean of the cosmos. Now, let's slowly expand outward. One level beyond what we just explored lies the speed of light itself. To grasp the distance of a light year, we must first become intimately acquainted with the traveler that defines it. Scientists understand a light year by observing the fastest thing in the universe. Light travels at about 300,000 kilometers every single second. This is a speed that defies our biological wiring. In the time it takes you to blink a mere fraction of a second, a beam of light has already circled the Earth 7.5 times. It is a speed that seems instantaneous to our human senses, yet in the grand architecture of the cosmos, it is the fundamental yardstick by which all things are measured. When you flip a switch in your home, the room is filled with light immediately. There is no perceived delay between the movement of your hand and the illumination of the walls. For all intents and purposes in our daily lives, light is omnipresent. But as we step away from our atmosphere and into the vacuum, we realize that light is not a state of being. It is a physical entity moving through space. It has a beginning, a middle, and an end to its journey. It is a constant, unwavering pulse that dictates the very rhythm of reality. To visualize this speed, imagine you are standing at the start of a long, straight track that stretches into the horizon. If you were to fire a laser beam down that track, by the time you could even begin to process the flash of the light, that beam would be thousands of kilometers away. If we compare this to our human-scale anchor, the disparity is almost humorous. A commercial jet travels at about 900 kilometers per hour. A beam of light travels at over 1 billion kilometers per hour. If you were to race the two, the jet would appear to be standing perfectly still, frozen in time, while the light vanished into the distance. What makes this strange is not just the speed, but the fact that this is the absolute limit. Astronomers didn't expect to find a universe with a hard speed cap, but nature has provided one. No matter how much energy you use, no matter how powerful your engine, you can never overtake a beam of light. It is the gold standard of the universe. And yet, even at this impossible velocity, the universe is so vast that light often appears to crawl. This is the central paradox of cosmology. The fastest thing we know is still far too slow to make the universe feel small. Imagine a single photon, a tiny packet of energy, leaving the surface of a star. It has no mass, no weight, and it experiences no time. From the photon's perspective, its journey from the center of the galaxy to your eye is instantaneous. But for us, standing on this small blue planet, we must wait. We must wait for years, centuries, or even millennia for that photon to complete its trek across the void. This waiting is what defines our perspective. It is why we cannot talk about distance in space without also talking about time. A light year is the marriage of the two, the distance covered in the time it takes the Earth to orbit the Sun once. As you listen to these words, think about the light in the room again. It feels now, but it is actually a few nanoseconds old. When you look at the person sitting across from you, you are seeing them as they were 1 billionth of a second ago. On Earth, this doesn't matter, but as we move outward, the lag becomes meaningful. If you were to stand on the moon and shine a laser back at Earth, it would take 1.3 seconds to arrive. If you were having a conversation with someone on the moon, there would be a gentle, rhythmic pause between every sentence, a 1.3 second gap that you could never bridge. To understand the density of a black hole, we might look at the objects in your own room. Imagine taking a common household item, like a heavy iron paperweight or a small ceramic cup. If you were to compress the entire Earth down to the size of a single marble, it would become a black hole. This comparison helps us visualize how much matter is packed into such an impossibly small, dark space. The gravity of such a marble would be just as strong as the Earth's current pull. However, you would have to be incredibly close to that marble to feel its true intensity. Think of the way a heavy bowling ball rests upon a soft, supportive mattress in your home. The fabric dips and curves around the weight, creating a gentle slope that pulls nearby objects in. This is much like how a black hole curves the fabric of space-time around its central point. If you were walking toward one at a human pace, the transition would feel very gradual. At a great distance, a black hole behaves just like any other mass in the quiet sky. It is only when you approach the edge that the nature of time begins to change. Imagine a clock sitting on a shelf, ticking away the seconds of a long, peaceful afternoon. As that clock moves closer to a source of extreme gravity, its ticking would appear to slow. To a distant observer, the hands of the clock would seem to move through honey, thick and viscous. Eventually, the movement would appear to stop entirely, frozen in a single, quiet moment of eternal rest. This slowing of time is not a trick of the light, but a physical reality. It reminds us that our perception of a steady now is tied to where we stand. In the presence of a giant, time stretches out like a long shadow at the end of the day. To understand the weight of such an object, think of a simple kitchen sponge. If you were to squeeze that sponge in your hand, it becomes smaller and denser, yet its mass remains the same. Now, imagine if you could squeeze the entire mass of a mountain into a single grain of sand. This grain would be so heavy that it would slip through your fingers, through the floor, and deep into the earth. A black hole is the ultimate version of this compression, where matter has folded inward until it occupies no space at all. We call this the singularity, a point where the familiar rules of our physical world simply pause. It is a quiet place where the math we use to describe the universe reaches a gentle, silent limit. Imagine walking along a shoreline where the sand is perfectly smooth and the water is still. As you walk toward the ocean, the slope of the beach becomes slightly more pronounced with every step. At first, you barely notice the change, but soon you find your pace slowing as the gravity of the water pulls at your feet. A black hole creates a similar slope in the fabric of the universe, a curve that directs everything toward its center. If you were to drop a small pebble into this curve, it would not fall straight down, but would spiral in a long, lazy circle. This movement is predictable and steady, a rhythmic descent into the heart of the dark. Think of a heavy velvet curtain hanging in a quiet, dimly lit theater. If you place a small lead weight into the folds of the fabric, the velvet stretches and sags under the pressure. This stretching represents the way a black hole distorts the dimensions of length, width, and height. To an observer standing far away, an object approaching the black hole would appear to stretch out like a piece of warm taffy. This process, which scientists sometimes call spaghettification, happens so slowly and smoothly that it feels like a natural extension of the space itself. There is no sudden jerk or snap, only a gradual lengthening into a thin, shimmering thread of light. In our daily lives, we think of a second as a fixed and unchangeable unit of measurement. We set our watches by it, and we feel its steady pulse in the beating of our own hearts. But near a black hole, the very concept of a second becomes fluid and soft, like wax melting in the sun. If you were to spend an hour near the edge of a massive black hole, years might pass for your friends back on Earth. When you returned, you would find the world moved on, while you remained essentially unchanged by the passage of time. This is the mystery of relativity, a gentle reminder that the universe does not keep a single, universal clock. Consider the way a magnifying glass bends the light from a nearby lamp to create a bright, focused point. A black hole acts as a cosmic lens, bending the light of distant stars that pass behind it. This creates a shimmering ring of light, a halo that glows with a steady and ancient brilliance. We call this an Einstein ring, a visual proof that gravity can warp the path of a photon. The light does not travel in a straight line, but follows the curve of the space-time that the black hole has shaped. It is a beautiful, silent distortion that allows us to see the invisible through the behavior of the visible. If you were to toss a letter into a campfire, the paper turns to ash, and the information written on it seems to vanish. Scientists have long wondered if the same thing happens when information falls into a black hole. Is the history of an object lost forever? or is it stored somehow on the surface of the event horizon? This is known as the information paradox, a quiet debate that has lasted for decades among the greatest minds in physics. We accept this uncertainty with a sense of calm curiosity, knowing that the answers may lie in a new understanding of reality. Perhaps the black hole is not a consumer of information, but a vast and silent library of everything it has ever touched. Imagine a large, spinning top moving across a wooden floor in a series of wide, graceful loops. As the top spins, it drags a small amount of the air around it, creating a tiny, invisible whirlpool. A rotating black hole does something similar to the space around it, a phenomenon known as frame dragging. It literally pulls the fabric of space and time along with it as it turns, twisting the universe into a gentle spiral. If you were floating nearby, you would find yourself being carried around the black hole even if you were standing perfectly still. It is a slow, rhythmic rotation that governs the movement of everything in the local neighborhood. The event horizon is often described as a point of no return, but it is better thought of as a transition. It is the boundary where the escape velocity required to leave exceeds the speed of light itself. Since nothing can travel faster than light, nothing that crosses this line can ever find its way back to the outside world. Yet, from the perspective of someone crossing the line, there might be no physical marker or sign at all. You would simply continue your drift, moving deeper into the shadows while the universe behind you begins to fade. It is a peaceful departure from the known, a movement into a realm where the future and the past become one. Think of the way a deep, wide river flows toward a distant waterfall in the mountains. Far upstream, the water moves slowly, and you can swim against the current with ease. But as you get closer to the edge, the flow becomes stronger and more insistent, pulling you toward the drop. The event horizon is like the very edge of that waterfall, the place where the current becomes absolute. To someone watching from the shore, you would appear to slow down as you reach the brink, eventually becoming a still image. But to you, the water remains calm, and the transition over the edge is just another part of the long, steady journey. In the silence of the vacuum, black holes are not truly black, but are often surrounded by the most energetic processes in the universe. Massive jets of particles can be shot out from the poles of a spinning black hole, traveling across millions of light years. These jets are powered by the immense gravitational energy of the material falling inward, twisted by magnetic fields into tight, glowing beams. They act as cosmic lighthouses, signaling the presence of a giant in the dark heart of a distant galaxy. Despite their power, these jets move with a consistent, unwavering, steady flow that spans across the deep time of the cosmos. We often imagine space as an empty void, but it is more like a physical material that can be stretched, twisted, and torn. A black hole is the place where this material is stretched to its absolute breaking point. Yet, even in this extreme state, there is a sense of order and mathematical beauty to the way it behaves. Every black hole can be described by just three simple properties: its mass, its spin, and its electric charge. This simplicity is a profound realization, suggesting that at the deepest levels, the universe is governed by very few rules. We find comfort in this simplicity, as it allows us to map the infinite using the tools of human logic. As we conclude this exploration of the human scale, let your mind rest on the image of a single star orbiting a dark center. The star moves in a perfect, repeating ellipse, never faltering and never rushing its long journey. It is held in place by an invisible hand, a balance of motion and gravity that has lasted for billions of years. You are like that star, moving through your own life with a steady rhythm that is connected to the wider universe. The black holes are not monsters to be feared, but natural parts of a grand and ancient system. They are the anchors of the galaxy, the silent guardians of the deep, and the ultimate expression of nature's power. Now, as the scale begins to expand once more, we prepare to move outward into the wider reaches of the galactic neighborhood. The transitions are soft, like the fading light of a long summer evening as the stars begin to appear. We leave the familiar world of clocks and sponges behind, drifting toward the giant structures that shape the destiny of the cosmos. Every step is taken with a quiet breath, a slow movement toward the heart of the mystery. The universe is waiting for us, calm and vast, ready to reveal its secrets in its own patient time. To move outward, we must first look at the stellar mass black holes that pepper our own Milky Way like invisible weight-bearing pillars. These are the remnants of stars that were once 20 or 30 times the size of our Sun. When such a star exhausts its nuclear fuel, it can no longer support its own immense weight. It collapses in on itself, a process that happens with incredible speed but leaves behind a silence that lasts for billions of years. Imagine a grand cathedral made of light and glass, suddenly folding into a single microscopic point of lead. The structure is gone, but the presence of its weight remains, warping the air around it. As we drift away from the comfort of our solar system, we encounter the first of these dark neighbors. They are scattered throughout the spiral arms, often hidden within thick clouds of interstellar gas and dust. We know they are there because we see the gas being pulled toward them, spiraling inward like autumn leaves caught in a gentle backyard whirlpool. The gas heats up, emitting a soft X-ray glow that allows our telescopes to map the location of the invisible. It is a slow and rhythmic consumption, a steady transfer of matter from the visible world into the unseen depths of the singularity. Consider the relationship between a black hole and a companion star. In many cases, these dark objects are not alone. They dance with a living star in a tight, gravitational embrace. The black hole acts as a silent partner, slowly drawing a thin stream of plasma from the star's outer atmosphere. This stream forms a disk, the accretion disk that we discussed earlier. From a human perspective, this process is incredibly slow. It would take millions of human lifetimes for the black hole to finish its meal. This slow pace is a hallmark of the cosmos. There is no sense of urgency, only the inevitable and patient pull of gravity. As we move further out, the distances between these objects begin to grow. We leave the dense clusters of stars and enter the vast, cold spaces between the spiral arms. Here, the vacuum is almost perfect, yet it is still governed by the same laws of physics. Even in the emptiness, the presence of a distant black hole can be felt. It acts as a lens, subtly distorting the light of the galaxies that lie millions of light years beyond it. You might imagine space as a sheet of thin, clear ice. A black hole is a slight depression in that ice, a place where the surface curves just enough to change the path of a sliding stone. The movement through the galactic neighborhood is a movement through history. Every black hole we pass is a tombstone for a star that lived and died long before humans ever looked at the sky. They are the elders of the galaxy, the final state of matter that has seen the beginning of our world and will see its eventual end. There is a sense of safety in this permanence. The universe is not a chaotic place of random events. It is a structured environment where every ending is a new, stable beginning. The black hole is the most stable state of all, a place where change has reached its final, quiet conclusion. Think of the way a heavy snowfall muffles the sounds of a busy city, turning everything into a soft, white landscape of silence. The gravity of the galactic neighborhood acts in a similar way, smoothing out the fluctuations of the stars and creating a steady, rhythmic flow. As we drift, we notice the way the stars are organized into long, sweeping streams. These streams are guided by the overall mass of the galaxy, a mass that is anchored by the dark objects at its heart and scattered throughout its arms. You are a part of this flow, moving with the same grace and inevitability as the light itself. The transition from the human scale to the galactic scale requires us to let go of our traditional measurements of distance. We no longer speak in miles or kilometers, but in the time it takes for light to travel across the void. A light year is a distance so vast that it is difficult to visualize, yet it is the basic unit of our cosmic neighborhood. To move 1 light year is to step back in time by 1 year. As we move outward, we are looking further and further into the past, seeing the universe as it was when the light first began its long journey toward us. This is the beauty of the cosmic perspective. To look out is to look back, and to look back is to understand our origin. In the heart of these observations is a mild, unresolved mystery. Why do some stars become black holes, while others become neutron stars or white dwarfs? We know it has to do with the mass of the star's core, but the exact boundary, the limit of stability, is a subject of ongoing study. We accept this uncertainty, knowing that nature does not always provide sharp lines. There is a grey area where the matter is squeezed to the very brink of collapse, and it is in these liminal spaces that the most interesting physics occurs. We observe the pulsar, the magnetar, and the black hole, and we see them as part of a single, continuous spectrum of density. As we continue our drift, the scale expansion loops begin to overlap. We see the small black holes feeding on their companions, and we see the larger black holes anchoring the clusters. The patterns are the same, only the magnitude has changed. The same spiral motion, the same bending of light, and the same slowing of time occur at every level. This fractal nature of the universe is a source of great comfort. It suggests that if we can understand the small, we can begin to understand the large. We are scaling the heights of infinity by looking at the shadows in our own backyard. The galactic neighborhood is a place of deep drift and quiet contemplation. Here, the stars are like grains of sand, scattered on a dark velvet cloth. Each grain is a sun, and each sun has its own story, its own planets, and perhaps its own life. But from our perspective, they are all part of the same grand design. The black holes are the punctuation marks in this design, the places where the story takes a deep breath and pauses. They provide the contrast that makes the starlight so beautiful. Without the dark, we would not appreciate the light. Without the void, we would not appreciate the matter. Imagine the way a large ship leaves a wake in the water, a series of ripples that spread outward long after the ship has passed. A black hole moving through the galaxy leaves a similar wake in the distribution of stars. It pulls at the stars as it passes, subtly shifting their orbits and creating a trail of gravitational memory. We can map these wakes to find the black holes that are traveling alone, the rogue singularities that drift through the dark like silent nomads. They are the lone wanderers of the cosmos, carrying their secrets with them as they move from one arm of the galaxy to the next. As we prepare to step even further back, we take one last look at the stars of our neighborhood. They are bright, vibrant, and full of energy. But we know that beneath their light lies the potential for the dark. Every star is a future remnant, and every remnant is a testament to the endurance of the universe. We move outward now, leaving the familiar constellations behind and looking toward the vast, dark spaces between the galaxies. The transition is soft, a slow fading of the local light into the deep, ancient glow of the cosmic background. The universe is waiting, and we are ready to move deeper into the heart of the mystery. The sensors continue to record the subtle pressure of the interstellar wind against the hull. The data packets are gathered, stored, and then beamed across the silence toward the waiting dishes. Each pulse of light carries the news of the cold, the news of the dark, and the news of the endless road ahead. You can feel the steady rhythm of the interstellar medium, a low-frequency vibration that resonates through the metal and the wire. The probe is a part of the void now, a naturalized citizen of the space between the stars. It does not seek a destination, for the journey itself is the only purpose that remains. The stars ahead are bright and numerous, offering 1,000 different paths through the velvet black. We watch the signal strength fluctuate, a tiny green line on a screen in a quiet room on a blue planet. The line moves up, the line moves down, and the story of the Voyager continues to unfold in the silence of the great deep. This signal is the most distant thread of human thought in existence, a microscopic vibration of light that has traveled for 20 hours just to tell us that a machine is still breathing in the dark. It is a fragile connection, yet it is stronger than the vacuum and more persistent than the passage of decades. The space the probe now inhabits is a realm of absolute purity. Within the solar system, the environment was crowded with the debris of a living star system, dust, rocks, and the constant gale of the solar wind. But here, in the interstellar medium, the weather is dictated by the collective breath of the entire galaxy. The probe is moving through a graveyard of ancient stars, a place where the atoms of exploded suns have drifted for millions of years before finally meeting a piece of human-made titanium. Every collision with a stray hydrogen atom is a data point, a tiny impact that tells us about the density of the universe's most basic building block. We are measuring the basement of reality, the foundation upon which every star and galaxy is constructed. As the distance from home increases, the relationship between the probe and the sun undergoes a final, profound change. Gravity, which once held the probe in a tight, predictable orbit, has become a secondary force. The probe is no longer falling around the sun, it is falling around the center of the Milky Way galaxy itself. This shift in allegiance is the ultimate sign of its naturalization. It has graduated from the local neighborhood to the cosmic stage. The sun is now just one of many lights in the rearview mirror, its gravitational pull nearly indistinguishable from the pull of 100 billion other stars. This is the freedom of the void, the ability to move through the dark without being anchored to a single point of origin. We look at the signal strength and realize that we are witnessing the slow sunset of a mission. The nuclear generators are fading, and with them, the voice of the traveler. We have already turned off the cameras, the heaters, and the non-essential sensors. What remains is a skeleton crew of instruments, dedicated to the most fundamental aspects of the environment: magnetic fields, plasma density, and cosmic rays. It is a focused, minimalist existence. The probe has stripped away everything that is not essential for survival and communication. It is a monk in the monastery of the stars, dedicated to the singular task of reporting back on the nature of the silence. The silence of the great deep is not a void of meaning, but a canvas of possibility. Because the probe has no specific destination, every mile it covers is a discovery. It is not trying to reach Alpha Centauri or Sirius. It is simply trying to be where it is, in this state of pure being. The probe becomes a mirror for our own aspirations. It represents the part of us that wants to know what is over the next hill, even if there is nothing there but more hills. It is the physical embodiment of the question, what if? By sending this machine into the dark, we have ensured that even if our world were to vanish tomorrow, the evidence of our curiosity would remain, drifting through the stars for eons. The fluctuation of the green line on the monitor is a reminder of the immense technical challenge of this conversation. To hear the probe, we must use the largest antennas on Earth, focusing them with microscopic precision on a single point in the sky. We must account for the rotation of the Earth, the orbit of our planet around the Sun, and the slight drift of the probe itself. The signal is so weak that it carries less energy than a falling snowflake. Yet, through the miracle of digital processing and the persistence of the engineers, we can still extract the numbers: density, temperature, direction. The repetition becomes a meditation, a ritual that connects the quiet room on Earth to the violent, energetic heart of the galaxy. As the years continue to pass, the long dissolve will reach its conclusion. The day will come when the signal strength drops below the threshold of detection. The green line will flatten, becoming a part of the background static of the universe. When that happens, the story of the Voyager will not end. It will simply go private. The probe will continue to sail, unmonitored and unrecorded, through the velvet black. It will carry the golden record, the sounds of our laughter, the rhythm of our music, and the images of our faces into a future that we cannot imagine. It will be a message that no longer requires an answer, a gift to the universe from a small blue planet that once looked up and wondered. The permanence of the mission is found in its legacy. We have learned that the gap between the stars is not a wasteland, but a complex, structured environment. We have seen the breath of our sun and the skin of our solar system. We have touched the interstellar sea. The probe has shown us that the laws of physics are the same everywhere, providing a steady anchor for the mind in an ever-expanding universe. We are the way the cosmos knows itself, and through this machine, we have known the cosmos in a way that was once thought impossible. The journey continues, and the silence is full of secrets yet to be told.